Hello, we're going to continue looking into more details of CUDA programming language and PTX, which is assembly language. Here we see in our first code in like the extension of the code that we have, our PTX code will be .ptx. And we can see here some of the first instructions where we have the version of PTX. We will have target, that is our microarchitecture. In my case is SM89, as I have Ada Lovelace stream multiprocessor microarchitecture. The address size, that this is um, the size in bits, whether pointers are 32 or 40 or 64 bits. In my case, I'm indicating 64 is wide and for more modern GPUs based on the architecture that I have. And then for the kernels, we will have to indicate visible. That entry, that will be the parameters of our kernel. Say we have a function to add numbers. This is the name of my kernel, and inside here I have the parameters, and here's the type of variable that this will be unsigned, 64 bits, and here we will have the parameters. So here we will have the different parameters of our kernel, as we can see here. And finally, we will just get out of the function with red, basically. So looking into details of this code, so we have the version of PTX, we have the GPU architecture, the kernel function is in entry, and the parameters are the kernel arguments. Looking into more of this code, we see that the threads that are in multiple dimensions in 3 dimensions, the X, Y, and Z, the threads IDs will be as follows. We have threads ID for each dimension, where we will have X, Y, and Z. This will be for our threads. Then we will have block ID, that it will be in this way. And we will have block dimension. It will be this way, that we will indicate our block dimension. In order to compute our global index that usually in CUDA programming we have as IDX, that we will do a mathematical operation that will be the index of the block X in the block dimension X, moving through the thread IDX. This will be to move in the X direction. To have an analogy of this CUDA code in our low-level intermediate representation PTX, we will need something like the following. So this instruction will be completely equivalent, where we will basically be indicating that we have unsigned 32 bits for to indicate our size of our variables in the registers. So we will need 3 registers that we will call with the percentage, and they are 1 or 2 or 3, etc., indicating our thread ID. That will be the way we call our threads IDs in PTX. We will have the block ID in the X direction, and we will have our block dimension in the X direction, and we will move these variables into this register. We will load them into these registers of unsigned 32 bits, and then to calculate this is multiply add operation. So in assembly, we will just call MET that will be multiply addition. We will only use the low bits of our result in the same type of variable that will be unsigned 32. We will call the register 4. That would be, in this case, IDX. That would be the equivalent of this variable. Here, we will call our R2 register. That R2 in this case is the block dimension, as we can see, the block ID, I mean. We will have the block ID. Then we will have our block dimension, that will be R3. And finally, R4 with the percentage sign. So this will be the same. Why this will be in the low bits? This could be because these are 32 registers. So this indicates that if we have 2 to the power of 32 operations and we are multiplying them, what it will be happening is due to arithmetics. What will happen is that this result will finally be unsigned 64 bits. So what we're doing here is that we are doing the multiply addition operation, and we are only storing the lowest bits in this register from this operation. This is what we'll be doing. So this is like an analogy of how it will be calculated our global index in assembly code in PTX.